In this video lecture, I will be doing some example problems involving impulse and momentum. So let's get started. Our book, as always, has a nice little strategy listed out in order to help us solve these problems. And we're going to do them for some simple problems so you get the idea of what to expect. And then if you keep following this procedure, when you do more complicated ones, it should help you not make mistakes. So as always, we're going to start with a picture, right? Step 1, draw a picture. 2, define your coordinate system and all of your symbols, right? Your mass, your V's, your initial, your final, blah, blah, blah. Make a nice organized table of known information and figure out what it is you're looking for. Look at that. It's actually nothing new. Okay, so let's see what this looks like in practice. A 500-kilogram rocket sled is coasting at 20 meters per second. It then turns on its rocket engines for 5 seconds with a thrust of 1,000 newtons. What is its final speed? So we're going to draw this. This is a rocket sled. It's kind of sled like this. There you are. He's doing the splits maybe, and it's got some fire outside of here. So he's got some initial velocity. His initial velocity is 20 meters per second. And he turns on his thrust. Now the thrust, remember, as he shoots the hot gases out from the behind, it applies a thrust force on the sled in the forward direction. That's F sub TH. And this velocity is going to increase to some final value. Initial and final. The thrust is to the right. It turns on its rocket engines for 5 seconds. That's our delta T. It's 5 seconds with a thrust, and we can consider this to be the average thrust. We're going to ignore the fact that when he first turns on and off the engines, there's a little bit of ramp up and slow down of that force. And we are asked to find the final speed. Okay, so we've got our picture. We're going to use the impulse momentum theorem that tells us that an impulse leads to a change in momentum. This, on the left-hand side, our impulse, well, it's to the right, so we have a positive average force times a time interval, delta t, and that's equal to the change in momentum. Now, technically, this is actually a change in the mass times the mass final times velocity final minus mass initial times velocity initial. So technically, actually, the mass of our rocket changes as he's burning fuel, but we can assume that the mass of the rocket is much bigger than the amount of mass that he's burning, combusting. And so we're going to take the two masses, the initial and final mass, to be the same. And that's going to be generally true for all the problems I give you, unless specifically stated that the mass changes. So this becomes the common mass times the final velocity minus the initial velocity. And I just realized I have an extra delta in here. We don't need that. The change in momentum is equal to the final mass times the final velocity minus the initial mass times the initial velocity. Okay. Okay, so we are looking for the final velocity. So let's solve this for V final. Divide both sides by M and then add V initial. So V final is equal to F average delta T divided by M plus V initial. If you want to go and do that in a couple steps, pause the video, make sure I did my math correctly, and now we're ready to plug in values. We have our average force, we have delta T. Do we have the mass? Oh, I forgot to write it in my table of knowns. We do indeed have our mass. It's 500 kilograms. So this equals average force is 1,000 newtons, 1, 2, 3 newtons, times delta T is 5 seconds, divided by a mass of 500 kilograms, plus the initial velocity of 20 meters per second. So V final is, we can do this, 5,000 divided by 500 is 50 divided by 5 is 10, right? Yeah, 10 plus 20. 10 plus 20 is 30. And then let's take a look at these units. Here I have a Newton times a second. A Newton is a mass with acceleration times a second divided by kilograms. Kilograms cancel. One of these cancels. And I'm left with meters per second in the first term. And I have meters per second in the second term. Gives me meters per second. So, does that make sense? Yes, it does indeed, because we do expect the rocket to speed up if it turns on its engines. All right. Let's do another example. Here we have a car traveling at 20 meters per second crashes into a bridge abutment. Estimate the force on a driver if he has a mass of 60 kilograms. If the driver is stopped by A, a 20-meter long row of water-filled barrels, or B, the crumple zone of her car, which is only about 1 meter. Assume a constant acceleration, and that's going to be true for both A and B. Okay, so how do we start? Well, we know that our car is traveling 20 meters per second, so here's our initial velocity. And the car is coming to a halt. Here's our final velocity, which should equal 0. We started at some initial position xi, and we ended up at some final position here, and our acceleration points to the left as we are slowing down. Okay, so let's work on our table of knowns. So we know the initial velocity is 20 meters per second. We have the mass here, but let's look at the kinematics a little bit, because we know we've defined a coordinate system. Here's our initial position. Let's call x initial equal to 0. Then our x final, well, it's either going to be 20 meters or 1 meter, depending on which problem we're on, A or B. What's our final velocity? If you said 0, you were correct, right? We're coming to a stop. The mass of my driver is 60 kilograms. Okay, is that everything? I've got the initial velocity, I've got the mass, I've got my initial and final positions. I think that's all that I know. Okay, so how am I going to figure this out? Well, I want to use the impulse momentum theorem. So I'm going to write that down. An impulse causes a change in momentum. Let's break this down. The left-hand side is our average force times some time interval is equal to mv final minus mv initial. Forgot to write down what I'm looking for. I'm looking for the average force. Okay, so I'm looking for the average force. Let's divide both sides by delta t. F average is equal to mv final minus mv initial over delta t. Well, I know my final velocity is 0 because I came to a stop. So this is simply negative mv initial over delta t. All right. Well, I have the mass of my driver. I have the initial velocity, but I don't know how long this collision is, and how long that collision is. The duration depends on whether I'm going into the water-filled barrels that you see on the side of the road, or if I just use the crumple zone of my car. So how can I find the duration? Well, I'm going to have to use kinematics to do that. So let's think. What are my kinematics equations? I've got 3 of them. I have x final is equal to x initial plus v initial delta t plus 1/2 a delta t squared. So my initial position is 0. I know my initial velocity, but I don't know the acceleration, so that's not going to help. I have v final is equal to v initial plus a delta t. Once again, I don't have acceleration or delta t. So that equation doesn't help. And lastly, I have v final squared minus v initial squared, and that's equal to 2a x final minus x initial. Okay, this one doesn't have time in it, but I can at least find the acceleration a and then use that and plug it back into one of these other ones. So I'm going to use the third equation and solve for a. So a, well, actually, let's put in our zeros. I know my initial position is 0 and my final velocity is 0. So a is equal to negative vi squared divided by 2 times x final. So it looks like I'm going to get a negative answer here from my acceleration, which does make sense. If I look at my picture, yes, my acceleration is to the left. Okay. So now I can find the time. I'm going to use equation 2 right here. I'm going to plug in this for the acceleration. So first I'll solve for delta t. Delta t is equal to v final minus v initial over a. Well, my final velocity is again 0. So this is negative v initial divided by a. Well, here's a. I'm going to flip this and plug it in here. That's 2x final, x, divided by negative v initial squared. Let's cancel one of these v initials. The minus turns into a plus, and I end up with 2 times x final over v initial. So as expected, the longer the final position is from the initial position, the longer the time interval, the longer it takes me to slow down. So, okay, that looks fine. Let me double check my notes. Yep, that looks pretty good. 2x final over v initial. Now I have my delta t. Now I can plug that in to the force to find the average force. So let's get purple. All right, so the last step is F average is equal to negative mv initial divided by delta t. So I'm going to take this and flip it and plug it in here. That's v initial over 2x final. Let's simplify this a little bit. Negative m times v initial squared over 2x final. My force looks like it's going to show up, end up being negative, which is fine because, as we expect, a negative force is what's slowing us down from the positive direction. And the one other thing that I'd like to point out is this quantity right here. What is that? Well, if we include the negative sign, this is the acceleration, right? See here, here's our acceleration, negative v squared, v initial squared over 2x final. So this is F is equal to ma, as we expected. So what we realized is that we could have actually simply used Newton's second law once we found the acceleration, instead of having to go through and use the impulse momentum theorem. These are two different ways of approaching this problem, and they both end up giving you the correct answer at the end. So let's plug in numbers. So our average force is equal to negative mass was 60 kilograms times v initial squared. My initial velocity, I think, was 20 meters per second. Square that, divided by 2x final. Now, x final for part A was 20 meters. And let's see, if I do this, 20 divided by 2 is 10. 10, that would be 600, I think. Meters per second squared gives me meters per second squared gives me a kilogram times a meter over second squared, which is, in fact, a Newton. So negative 600 newtons. Now, if I have, that's for part A. For part B, if I plug in only 1 meter here, the average force is equal to negative 60 kilograms times 20 meters per second squared divided by 2 times 1 meter. So that's 400 divided by 2 is 200. 200, 2,000, 2,000, 120, is that 120,000 newtons, same units as before with the negative sign, let's not forget that. And this makes sense, right? The If the distance we're traveling is 20 times greater, the force of impact is going to be 20 times less. So you can double check my math on this.